Hello, everybody. Hello. Yeah, that's the only time I'm going to use that microphone. But I guess we'll get started. It's about 1 p.m. This talk's going to probably go long because there's a lot to talk about, and I really hope that y'all have interesting questions for me at the end. But without further ado, let's get this started. So first of all, who am I? My name's Chris. I'm doing a talk on turning domain data into domain intelligence. I'm the founder of dnstrace.pro, which is actually the project that does all of this. So I'm pretty much just talking about my life for like 2 hours. I'm a third-year RIT student in the computing security department, which I'm very happy to be participating in. It's an awesome place, awesome people. Shout out to 4 professors in particular: Robert Olson, Bill Stackpole, Garrett Akarachi, Jonathan Weissman. I don't think any of y'all are in the building, but thank you, acknowledgements. I would applaud, but there are literally none of them here, so okay. So be it. And I'm a big geek. I run Snort on my own network. I love guacamole. I'm a Dungeons and Dragons GM in what little spare time I have. And I'm not really here presenting as an expert. And I want that to be acknowledged from the outset. At the end, we won't really have a question and answer session so much as a questions, comments, concerns, and corrections section. I'm coming to you as somebody who spent a lot of time working with DNS and domain data. You're free to tell me I'm wrong about something, and we'll figure it out. I have a notepad up with me and a pen. Let's figure it out. So the contents of this talk are broken down into 7 little sections. First of all, a quick refresher. I know, I'm sorry. Second of all, the reactive threat intelligence problem, really evaluating what kind of security issues there are with turning DNS into a secure service for consumers. And then we're going to start trying to fix that problem, of course. So we're going to look into scraping and ingesting DNS data. We're going to look at anomalies and analysis that we've found so far. We're going to then try to figure out if we can achieve proactive intelligence instead of just reactive intelligence. But we'll talk about that in section 1, technically. And then we'll talk a little bit about limitations, future improvements, and then open the floor up to discussion. So this is going to be a very domain-centric talk. And yeah, everybody hates DNS. That's okay. I do too. I work with it all the time. It is not fun. So just for the people that might be new in the room, please work clicker. Okay, thank you. So if you have a link, you have https://www.facebook.com/login/. The protocol is HTTPS. We don't need it. That's not relevant to this talk. The page, login, we don't need it. That's not relevant to this talk. What really counts is www.facebook.com, which is a fully qualified domain name. And it's broken down into certain parts. Facebook.com breaks down into 3 distinct parts: top-level domain or suffix, in this case com, registrable domain, which is Facebook, that's the one that Facebook actually owns, and then subdomains, that's the free domain space that Facebook gets for owning Facebook.com. And what can it tell you? DNS houses a lot of information. It tells your computer how to get to places using IPv4 and IPv6 addresses. It tells your computer canonical names, like where you should actually be going instead of going here. It tells you MX records for mail, NS records for name servers, text records if you really want to. You can configure geographic data to be served by the domain system. Why? I don't know, but you can. And of course, you can use a request called any to try to get all of this for a given fully qualified domain name. We'll talk about that later. And how does it work? You make a request to your DNS. This is assuming a recursive query that's then to your DNS, which is a recursive query that's then solved by iterative queries. You send a request out to your DNS goes to the root DNS, and you're like, hey, this guy wants to go to facebook.com, how do we find .com? And then, you get a reply saying this is how you get to .com. Your DNS asks .com how to get to Facebook's name server. Your DNS then goes to Facebook's name server and says, how do I actually get this person to www.facebook.com? And it's a hierarchy. This is a hierarchical system. And there's no point that any of these DNS servers are obligated to expose any more information than the information that you specifically requested. They're not going to tell you everything about Facebook or everything about com. They probably will tell you all the top-level domains, but we'll talk about that later too. But anyway, it makes this kind of closed. Since there's this hierarchy and nobody's obligated to tell you anything that you haven't already figured out something about, for example, a fully qualified domain name, it's hard to get some data out. And now we're going to talk about how DNS security works for the consumer. For example, if a domain is seen doing something bad, like distributing malware, for example, what kind of security intelligence do we have there to protect the end user? And we have some real problems, first of all. And let's consider, for example, let's realize, for example, that reactive security is not great security. And let's consider file-based antivirus, file signature-based antivirus, that is just 100% based on signatures. Malware author generates some malware. The antivirus authors catch a copy of that malware. They analyze it. They get a signature. They publish that signature to all other users of their product. In the meantime, the malware authors generated 5, 10, 50 more files with different signatures by making small changes to code or making polymorphic code. So it's really, really easy for people to circumvent. And it's purely reactive, so it's difficult and costly to maintain. For every new file that comes in, you have to develop a new signature, and then you have to publish those. And in that time, your users are getting infected all over the place. This is the kind of status that malware was at in 2000, 2005. It's not great. It's better than nothing, don't get me wrong, but it's not great. And things did get better for anti-malware programs. They got a lot better. We now have heuristic analysis. But do we have that for the domain space? And here's a quote from Symantec. An IP address earns a negative reputation when Symantec detects suspicious activity, such as spam or viruses originating from that address. That sounds like purely reactive security to me. Now, when do you think that this was published? If you guessed last night, the answer would have been, not surprising. This is the kind of status that a lot of security companies are at when looking at the domain space and trying to proactively block threats at a network level. Here's a little bit better. If the IP addresses change frequently and if the site has an IP address that was hosting malicious content in the past, it can result in a poor web reputation. Now this is from Cisco Talos. And this is actually a really great step forward because they're starting to use heuristics. So they've noticed that malicious domains tend to change IP addresses a lot more frequently than non-malicious domains do. Now, that is a good start. And domain safety heuristics are available, and they do help. You can look at how recent the registration was because malware authors tend to burn through a lot of domains very, very quickly. You can look for frequent address changes, as Talos does. You can get estimates on popularity if you have that kind of footprint on the internet, which, of course, this being I am a college student, we do not. And what can we do to improve this? So consider the following. There exist systems that are relational learning systems. These systems can predict unforeseen or future relationships between entities based on past observations. And you can see really good examples of them down here. They tend to be directed or undirected graphs with a very set structure, and they are typically very interconnected. Now, we can't really do this for malware. Malware has too many dimensions. It can be too many things. You can't classify it as easily as you can other data. So malware X does 50 different things, and malware Y might do 200 different things. And just classifying that much is going to be a huge investment. And then what are you going to get out of it? You're not going to get a huge amount, unfortunately. But domains. Well, domains have a very fixed structure. It's very, very strongly ingrained into the domain name system. There are only a certain number of things that a domain can be. It resolves to certain IPs, it resolves to certain other domains, it has certain records of certain contents, and that's pretty much it. So what if we tried to apply relational learning to the domain space? Well, we're going to need a lot more than just, say, a list of some domains. You need to have a huge quantity of parsed domain data. You need to have fully qualified domain names. You need to have subdomains. You need to have pretty much all TLDs. You need to be getting everything that those resolve to as well, because you have to build the interconnected graphs. And you're not going to be able to connect Facebook.com to Yahoo.com without a little bit of an IP. And some collect this passively. There are big repositories of domain data, for example, DNSDB that's run by Farsight. We don't have, again, the resources to do that. We can't establish a passive tap where we get 2.7 billion data points per day just by observing the kind of DNS traffic that goes through the world. We have to acquire this kind of data aggressively. We have to perform the queries. We have to figure out what goes where on our own. And we need as much threat intelligence as possible to go with that. It doesn't do you any good to notice that yahoo.com and malware.ru go to the same place if you don't realize that malware.ru is malicious. You need to be able to figure that out so you can see this information into the relational intelligence systems that we create. And then, of course, you need to make it responsive, because it's not very useful to have a graph database that tends, 30 minutes to render a small graph with upwards of, like 500 but less than 1,000 nodes. And then you need real methods of analysis. You can't just say, well, this touches one other malicious thing, it's probably bad. You see a lot of stuff get flagged. You're going to have a lot of things going to certain places. For example, if you're looking at a hosting provider, there could be a ton of domains pointed at one IP. And if one of those domains is malicious and you automatically flag everything else, you're going to have a huge false positive rate. So you need to figure out in a quantifiable manner how you're going to evaluate these graphs to generate real intelligence that is not just, okay, well, it's getting somewhere near something malicious, so out with that. So let's get into it. The first thing that we need to do is acquire a list of TLDs. Well, you can go to data.iana.org and get a list of all TLDs. Congratulations, that's the easiest part of this entire talk. Currently, there are 1,543 top-level domains active. This list is available by HTTP and by FTP if you do so desire. Great, okay, this wasn't really a challenge. Now, acquiring domains is going to be a little bit harder. So each top-level domain has a zone file, and that zone file contains a list of all the domains and also all of the name servers for those domains. And you can buy access to zone files through certain providers for about $300 per year, which seems to be a reasonable price for anybody who isn't a student and skint broke. And that's my ramen money, so we're not going to do that. You could alternatively request access to zone files from those registrars directly. So pretty much circumventing the middleman that aggregates that zone data and going straight to the registrar and being like, hey, I'd like to see your .com zone file, please. And a lot of them will say, yes, that's fine, as long as you're using it for a real problem-solving thing, or you're doing valid research, or you're an academic. And a lot of them will say, great. Some of them won't, such as Yahoo, Zappos, etc., which all run their own top-level domains and will not let you touch them. And if you wanted to do this kind of thing in bulk, you can go to ICANN CZDS, which is the Centralized Zone Domain Service. Zone Data Service, my apologies. And you can actually bulk request for, I think it's 500 or more zone files with like a single form. It's awesome. Now we get into the real problems. So we've gone down the hierarchy from the root to top-level domains to domains. Now we have to figure out, with all of those domains, how do we get those subdomains? And I'll give you a hint. They're not so kindly, regarding people requesting access to their zone files. Unfortunately, that's just how it is for a lot of companies. Facebook doesn't see the real value in exposing the facebook.com zone file to me, a researcher. Even if it's for a good purpose, they like to keep stuff private, and that's fine. So we're just going to discover things out, anyway. Now, there are certain things that are going to be out of scope. I'm going to just talk about like how you could do this if you wanted to, and why we're not going to do that, and give you some examples of tools that you could use. There are going to be other things that are in scope that we'll actually do demos of. I have the demos pre-recorded because I don't trust the Wi-Fi. They're really nice GIFs, I promise. So first of all, you could try to brute force look up something. You go to facebook.com, you point dig at it, and then you write a quick little script to generate every possible subdomain from A to Z. Absolutely not. That is a great way to have somebody knocking on your door asking who the legal resident is because you're being served papers. A good lawyer can make this look like a denial of service attack. And if you tried to do it at scale, which we are going to try to do, a good lawyer, actually a bad lawyer, could make it look like a distributed denial of service attack. You don't want to do this. And if this is the first thing on your list to try, shut down your machine, take a breather, get a monster. You can figure out a better method. A good way of doing this in normal engagements would be to crawl a website. If your domain that you're investigating has a website online anywhere that you can see, you might as well just go on there and follow as many links as possible. It's fairly complex and resource intensive at scale if you're rendering the entire document, but it's definitely a possibility. And you can do this with Skipfish, WebScarab, etc. There are a lot of great options to do this, and I do recommend it for your own engagements, but not here. And we could also do, looking things up in search engines and passive DNS. And again, this is great for real-life engagements. I actually strongly recommend this as a starting point to just identify possible areas of scope for any engagement that you might be going into. And you can use Sublister, which is built into Kali for this. It's phenomenal. Just give it a domain, and it will find everything. Google, Yahoo, Bing, passive DNS, etc. But this depends on external services. And those external services are going to blacklist us if all of a sudden we have 1,000 queries per second hitting them. So that's out. Now let's start to evaluate what might be in scope. Now, brute force wasn't a great idea, but what if you did a probabilistic lookup? There are certain domains and subdomains that tend to show up more frequently than others. For example, www or mail or things like that. So if you were to perform lookups on things that you suspect are more likely to be present than not, that could really help cut down on the search space. And you can combine that with anything that you've generated, say a word list off the website that you just scraped, to cut that down even further. And you can actually enumerate my site using some software that I wrote for Robert Olson's class with 596 queries total, just based off Rapid7's forward DNS dataset. So parse Rapid7 down. I actually provide this in the GitHub, but you parse it down to the most common subdomains. You count them, you sort them by the frequency, and then you run through until you run out. And so here's that software, here's that available software running in default mode with the default list. I'm just saying, hey, we're going to enumerate this domain using A records. And you give it a couple seconds. 1, 2, 3, 4, 5, 6. So please, come on. There we go. And that's all of the subdomains that were present for my domain at the time, enumerated in 596 queries exactly. It takes about 10 seconds. It's a single-threaded program. I wrote it in like an hour. You can write something much better to get that time much farther down, and things will work out fairly well for you. Now, you can also do reverse DNS, which is a simple little dig query, just the -x. And it's useful for IPv4 addresses. Pretty much you're taking an IPv4 address, you're saying, hey, domain name services, what domain goes here? But unfortunately, that usually ends up in ISP assigned addresses, not really anything of use. So, the dig plus short for 121.73.62.2 ends up with something .cable.telstraclear.net. Doesn't tell us anything. So it's something that we're not going to not use, but it's not something that's going to give us a huge amount of data. Now let's talk for a moment about DNSSEC. DNSSEC is a set of security extensions for DNS. It provides 3 main things. Origin authentication, so you know that the reply is coming from a name server of authority. It provides data integrity, so you know that the reply that you're getting is actually the correct reply. There's been no errors in transit, etc. And you also get authenticated denial of existence. Denial of existence. How did they make that work? So what they actually ended up doing for denial of existence is they implemented a record called NSEC. And NSEC is pretty much the next secure record, which in a lot of cases tends to be the next record that exists. So if you request test.example.com, which clearly does not exist, the name server will reply that the next secure record is www.example.com. Oh boy, that's phenomenal. And you can see, you can test things out right here, and if you look very closely, you'll see 164 in NSEC, www.example.com, and you get exactly what the query is going to look like. And then you can just query for that, and then query for the next thing that probably doesn't exist. And either you'll get a response, and cool, it exists, or you don't get a response, and you understand the next secure record. And then you have the next target to enumerate. It's awesome. And you can do this with tools like NSEC 3map, which, for being a proof of concept tool, has a lot of really nice options. This is available on GitHub. It's not mine, but it's available on GitHub, and it's awesome. And we're going to, per se, use NSEC to enumerate PayPal. And would you look at that? There's all of the subdomains for PayPal in, oh, that'll take, I don't know, 2 more seconds. 1 Mississippi, 2 Mississippi. Okay, it's closer to 3. But anyway, with a mere 689 queries, we've now enumerated the entire subdomain space of PayPal. Now, to circle back a little bit and just reiterate how bad brute force is, if you wanted to do that, just plain old naive brute force, that would have, I believe the word was septendecillion. Are there any mathematicians in there? It's like 10 to the 55. It's ridiculous, the amount of queries that you would have to perform. And that is the query throughput of Google for several millennia, probably until the end of time. It's a lot of stuff. So techniques like this can really cut down on the resources required to enumerate a domain in its entirety. Now, some people very quickly noticed that that was a bad idea. And so revised DNSSEC standard came out that introduced the NSEC 3 record. And that improves privacy, but doesn't solve the problem completely. So pretty much instead of when you request test.example.com, instead of replying with www.example.com as the next secure record, it says that there is a secure record before this and past this, and it presents the hashed values of those subdomains. Now, that is frustrating. Doing an NSEC 3 lookup on 0x0potato.de, which clearly does not exist, but is secured with NSEC 3, produces nothing of use. I mean, if you can figure out just by looking at that screenshot what the next secure record is in plain text, you're a god and you should be presenting, not me. But it's hashed, and these tend to be fairly short because www, even if you're guessing every possible character, the possible combinations for 3 characters on your local machine is pretty low. So what we do is we enumerate the NSEC 3 secured domain, figuring out all of the, there is nothing between X hash and Y hash. You can still enumerate all of those hashes, not the domains themselves, but the hashes. And then what you can do is you can throw that into Hashcat if you really wanted to. And I did really want to, so I compiled OpenGL for my Xeon CPU, and I threw Hashcat at it at the .de top-level domain zone file that I've just enumerated. And after a mere couple seconds, we're already up to 11% discovered. This is using a very, very naive mask. It's not very useful. It's not very fast, but with a little bit of tuning, this could actually be a viable way of enumerating domains, especially if you have, per se, several GPUs, which the system did not. But that still wasn't enough for some people. So if you are Cloudflare, and by the way, if there are any Cloudflare guys in the audience, you're the bane of my existence. Because they've implemented something like this, where instead of assuming that the next secure record is going to be a record that exists, it will generate records on the fly that are garbage records. And you'll see, running through this again, we get nothing. There's an existing domain A, B, C, D, E, F. What are these? They're not mine. But you know, Cloudflare says that this stuff exists, and all of a sudden enumeration is no better than brute force. Great job, Cloudflare. Whoops for me. But going through a recap here, if you are in engagement with somebody who has a DNSSEC DNSSEC enabled site, enumerate it. You lose very little by attempting an NSEC or NSEC 3 walk. Worst case scenario, you find out that they've secured it with Cloudflare or similar improved DNSSEC methods where they return garbage NSEC responses. And you know, oh well, you've lost 5 minutes of time. But if it does work, you've suddenly enumerated their entire domain space, and that's phenomenal. NSEC 5 is on the way. NSEC 5 introduces certain improvements that makes it such that people cannot do walks whatsoever by default. And you know, for my project's sake, hopefully it doesn't reach mass adoption anytime soon, because I like being able to do NSEC walks. But another thing that you can do to enumerate domains is, of course, a zone transfer. You can politely ask the zone owner, Facebook's name server, like, hey, can you please give me the zone file? And there are very few reasons to have this enabled, but some people still do. Between 1 in 7 and 1 in 10 domains has a name server that will actually allow you to perform a zone transfer. So all of a sudden, you don't just get, a list of subdomains, though in this case, it was very funny to have a list of all the North Korean domains as of September 2016, which is phenomenal, by the way. One entire country, 28 domains. Great. But you can perform an AXFR with very, very little resource investment. And all of a sudden, you get everything in the zone. So here we're going to do a little test zone transfer against zonetransfer.me, which is a great place to test your zone transfer skills. And we get everything. We not only get the domains, the subdomains, we get A records, MX, NS, server, everything we could possibly want. And we are starting to get into the next stage of the project, which is not just not just fully qualified domain names, but actually getting domain data. Where does this go? And that's great, but we're really only halfway there. Now we have to resolve the domain space. So we have a list of, let's say, 1 billion, for example, 1 billion fully qualified domain names. We've parsed them down into subdomains, into domains, into suffixes. But we need to actually figure out if there's any more going on, as well as trying to figure out, well, where does this go? What A records, what MX records, what NS records? You know, what are all of the characteristics of this domain so we can link it to other domains? And the way that we're going to go about this is we're going to DIY it. We're going to try a zone transfer. We're going to try any queries, which, again, Cloudflare people in the audience, you're the bane of my existence, because Cloudflare has deprecated the any query, also known as they've stopped responding to them, which apparently if you're an internet company that's large enough means that you're officially deprecating it. So they are not responding to any queries anymore. That's no longer a viable way of enumerating any sort of data. They just reply with another garbage response, which is to be fair, I might be complaining about Cloudflare a lot. I understand the decisions that they've made here, and I understand that any queries are really, really useful, for example, denial of service amplification. But, you know, it's frustrating for me as somebody who would actually like to use the any query instead of having to enumerate, you know, option number 3, iterating through every single desired query type for every single fully qualified domain name that we have in the database. But if that's what it comes down to, that's what it comes down to. And we're going to thread this because each domain is independent, and we're going to geographically distribute it such that we might be able to pick up on interesting little things, like misconfigurations or places that should reply but aren't replying and things like that. And of course, there is really no excuse not to use the data that others provide. For example, Rapid7's Sonar project, they actually publish several billion data points per week of scans that they've performed off Amazon AWS, resolving all of the forward DNS names that they know of, looking into a continuation of SSL Observatory, and also looking into reverse DNS, which is something that we talked about previously. They do all of those queries on a weekly basis. Why would we? We can just harvest it from them. And they permit non-malicious, non-commercial use. Now, I'm using this for non-malicious purposes. What you do with the service is entirely up to you, but we'll try to keep it clean. And then, of course, we have to store everything. So we are coming into possession of several hundred gigabytes of data every week. How are you going to store and organize that in a way that you can actually query against it? The answer for us is scalable database solutions. We ended up, after many trials and errors, with Percona 5.6 MySQL drop-in variant with TokuDB running as a backend, which has actually scaled fairly well to our solution, unlike InnoDB, which pretty much folded after a certain period of time. TokuDB has well resisted all of the challenges that we've thrown at it. So I do recommend it for large data projects that you might be looking into a storage method for. And compression works wonders. This is all textual data. You have no reason to not use compression. I know you've compressed a movie once, it didn't do anything. This is text data, it works awesome. We use low compression settings, we get about 2/3 space savings. It's awesome. No impact on performance time either. Great. And if you're querying against it, index, 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 index. Anything you're querying against, you should have an index, because otherwise you're doing a full table scan, and you do not want to do a full table scan on 1.3 billion rows of data, for example. So let's get into the really fun parts. We have a lot of data. Let's analyze it. Whoops, I should have probably deleted that. Oh well. Anyway, so first of all, we have some interesting domain errors that we've come across. Things that we couldn't parse using our internal tools. And I'm not really sure, because I am not an authority, but I'm relatively confident that there is no top-level domain called DEPL 152.1945933. Any corrections? No, doesn't seem like a registrable top-level domain. And so you come across interesting issues like that, again with a .AE0152. No idea how this ends up happening. And then you get into an interesting one, DC-WPProd-F5. If anybody has any ideas as to what that is, I'd love to hear them. The idea that came closest to my mind when I was looking at that was F5 Big IP Application Accelerators. Okay, I'm getting some nods, but okay, who knows? And then we actually came up against some very odd results that actually really baffled me for a while. Nick.LLC and Mac.sport. Well, that seems like it should be valid. And IANA says yes. IANA says yes for LLC. It also says yes for sport. These are TLDs that exist. Nick is a fine domain name that meets criteria. The criteria are very low, but it meets them. But Mozilla's public suffix list says no. And that's actually a problem. So We use Mozilla's public suffix list internally to figure out what a registrable domain is. Because if you take the naive approach of saying like www.facebook.com, www is the subdomain, Facebook is the registrable domain, .com is the top level domain, well, we're just going to explode on the periods and then take the last value, and that's the top level domain, that's the suffix, and then anything after that directly is the registrable domain. Sounds great. And then you hit a site like darknet.co.uk. If you apply the same logic, you're going to end up with .co as your registrable domain and darknet as your subdomain. So you actually can't split them naively. You have to use a suffix list that will allow you to separate things into what is most likely and what is not most likely a registrable domain based on the suffixes that are currently available. The largest of which is the Mozilla public suffix list. It's available for free. You can find it on GitHub or publicsuffix.org or things like that. And it's actually the list that a lot of browsers use to determine where user cookies can be set. Because you can set a cookie for your subdomain or for your domain. And if Mozilla's public suffix list is having some trouble figuring out what the registrable domain is, that should be the maximum level that somebody can set a cookie for, all of a sudden you can set super cookies that expand way beyond what you should reasonably be able to set data for. And that's very bad. And I've actually poked the dragon, and I've submitted a GitHub issue, and it's the first GitHub issue that I've ended up submitting ever, actually, to any company that is not me. So the public suffix list is actually missing a couple IANA recognized top level domains, and I want to figure out what's going on with that. They haven't responded yet. We'll find out. We've also seen some interesting invalid types. Ooh, I notice I'm running low on time. We're going to burn through this. So we've noticed some interesting invalid types. For example, a query type was returned to us as A104-100-169. I can keep going. It doesn't really seem like a thing that exists when normally a type for a DNS query is A or quad A or CNAME. Who knows? It returned some interesting values. It actually returned a link to an EC2 instance and then said that it was an A record. Interesting. And then we had dc-wp-prod-f5 appear again, and it appeared talking about canam.ws. If any of you want to investigate into that and tell canam.ws that they might have a F5 big IP application accelerator that's acting a little haywire, you definitely could. And now let's look into stats. So with the IPv4 address space, the DNSA replies, we actually found a fairly significant use of private IP space. So these are private IP replies on public DNS space, which is not necessarily good. And honestly, it was a very small percentage of all of the replies that we got, hovering around 0.1%. But that's pretty huge when you consider that 0.1% can be, several million replies that are exposing private IP mappings to the public IPs, or the public DNS space. So there's actually a huge amount of use of loopback. The follower was 10.0, 10.0.0.0/8, and then a couple other notables that had a really good amount of data being exposed. So definitely something to look into. And you hear a lot, Google's touted, 20% of people visiting our service are using IPv6. That's great and all. Only about 1.1% of domains that we knew about actually resolved anywhere in the IPv6 space. Everything else was IPv4. And that's a holdover to how slow the DNS system is with updates. How slow people might be moving their services over to IPv6 enabled servers, data centers, etc. It is what it is, and it's an interesting looking glass into the IPv4 to IPv6 transition. We also got some interesting CNAME mistakes. Just for reference, if you're putting HTTP into your canonical name DNS record, that's not how it works. Unfortunately, you have to keep things within the DNS space only. So You get some interesting responses here. We actually saw a huge number that had a CNAME that seemed to be some sort of hash, like the 6CA, OFE, etc. response. Again, oddities. If any of you want access to this data, access to the database, let me know. You're free to do your own research with this kind of stuff. We also get the occasional little keyboard smash that is at the bottom. FD, 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 FDF. Great, good job. An administrator got very bored. And we also get the occasional little mishap where somebody forgets the dot in .com. It happens. And we actually see that a lot of people point their MX or NS records to localhost, which doesn't work out on the public internet, but that's the kind of stuff that we see. It amounted for nearly 1% of MX and NS queries that we actually got a reply to. So pretty interesting there. It's probably a default on certain systems, which is why we see this level so high. But again, if you want to receive mail, you probably need to set something other than localhost. So now we have a huge amount of data. What do we do with this? How are we going to work with this? We have to then map this together into these great spanning graphs. And how are they even going to tell us stuff? Well, first of all, we need to add threat intelligence. I talked about it a little bit at the beginning, and then you probably forgot about it. But by adding more and more threat intelligence, we can really get a greater view into the security of DNS space, and we can get better information about what clusters of DNS information we should be labeling are bad versus good. And we ingest as many feeds as possible. We ingest phishing feeds from OpenFish and other sources like that, domain reputation feeds. We ingest IP reputation feeds. We ingest the Bogon reference from Team Simru. Is that even how I say it? I don't know. It's awesome though. And we are considering heuristics. Like the approach that Cisco Talos had, there's really no reason not to try to evaluate the heuristic data that we can get for a domain. Of course, we're not going to be able to get our hands on popularity data for a domain, but we might be able to figure out things like when was it registered, who was it registered to, what kind of activity has it had, like moving around. This kind of stuff can be used to more accurately establish what is and is not malicious and filter out both false positives as well as false negatives. And we want to be able to tune this. So we check the Intel's reputation like itself. For example, we're more likely to trust a FireEye threat source than a wally3k.github.io and that kind of stuff. And we also look at the threat type and severity, and we rate both of those on a scale of 1 to 5. And then for users who are eventually generating lists with that, we'll add a user bias, which is a multiplier. So you can say, well, I don't actually really care about not going to the Pirate Bay, but I do definitely care about grandma getting hit with an exploit kit. And with all of that said, we finally get to the graphs with like 5 minutes remaining. Here are the graphs. So this is a map of a hosting provider. The redder nodes are malicious. The yellower nodes are less malicious. We're actually going to zoom in a little bit here so you can see that there are a lot of malicious nodes pointing to given IPs with given CNAME. And then you notice one yellow node, Adobe update.top, which is not flagged. And that's the kind of domain that we're looking for. This is the kind of proactive intelligence that we want to generate. We want to be able to figure out Adobe update.top is malicious before grandma goes to it. And sometimes that's going to be really hard. You can generate more graphs. They're very intricate. They're frustrating to work with. And there are times when you look at the graph and you get a net, just this absolute cluster of information that's very, very difficult to interpret. And we need to build a machine that can interpret that effectively. And honestly, we're still working on it because there are some times where the threat intelligence that we get is not so great. j.maxmind.com probably shouldn't be read. It's used by some malware to figure out the geolocation of a given target, but it's also used by legitimate services to do the same exact thing. Why is it blocked? Who knows? And we need to be able to do this at scale and reduce false positives. This is AWS, by the way. This is a subset of AWS. I could only generate a subset of AWS. This is not all of AWS because the graphing engine that I have for this crashed. so this is a subset of AWS. And this is a subset of GitHub.io. And we have to figure out, there are some red dots in here. There's some things that we definitely do need to block, but there are going to be others that get caught in the crossfire if we apply naive approaches. So what we're considering very strongly is frequency. What percentage of nodes resolving to this IP are malicious? And that's a really great starting point for us. And it won't solve all the problems. And there's a lot to improve here, unfortunately. The data is far from complete. We have about 2 billion data points in system right now, but that's not enough. We're not covering enough of the domain space. We haven't enumerated all of the possible subdomains. We're not looking at all of the possible data that we can possibly get. And it's the same problem with our threat intelligence. Our sources are good, not great. We're working on we have to work off free intelligence. We have to work off free sources. This is an academic project. It's not got the insight that FireEye has. And our response time due to that is actually fairly slow. Of course, the graph engine needs work, like I've just said, and it's really only useful as a post-mortem investigation tool. That's not really what we want for it. And actually, here's a distribution of where we do our scanning from. Sweden, Canada, United States. That's not coverage. We're not covering the entire world, and we really need to. This needs to click too. And so we have a lot of stuff to work on. We need to talk to a lawyer. I need to talk to a lawyer. I really need to talk to a lawyer because Robert Olson, who I now see has shown up in the back. Hi, Rob Olson. There was a round of applause waiting for you at the end. It's half yours, it's half mine. We need to talk to a lawyer to figure out, can we actually use this data in a way that is useful? Because I am a lot easier of a target for somebody to go after than, per se, Rapid7. Rapid7 has lawyers. I do not. So if somebody wanted to say, hey, you're not allowed to do this, give me your money. What am I going to say? No? We'll see. So we also need to scale out, cover more geographic areas, increase our query throughput. We have capped out at about 1,000 queries per second, which is pretty solid until you consider the scale of the domain space. We need to ramp up those numbers, and you can help. We're actually releasing software that allows people to use their systems as resolvers for our system. It'll take some of that extra internet throughput that you have, use it to hit Cloudflare DNS servers. I've talked to them about this. They say it's okay. You can hit Cloudflare, get lists from us of things to resolve. You send those resolved lists back. Cool. We ingest more data. And the more data we ingest, the more of an intelligent system we can create. And we need to implement certain things that we talked about today, such as NSEC walking and transfers. We want to implement NSEC walking in a way that doesn't appear like it's a denial of service attack. We want to implement AXFRs in a way that you can actually parse them, because parsing domain data is actually really frustrating. And the end game of this entire project, as I come up 2 minutes to the end, we want to make dnstrace a proactive tool for geeks like me, like you, like all of us here. We want to generate firewall configurations. We want to generate DNS block lists, things that you can toss at the pie hole that you have sitting at home, that you can block threats before they actually reach your network, which could be awesome. And most of all, we want to make this tool a proactive tool for everyone. We want to make this protecting grandma for free, if we can, hopefully. We want to potentially create browser extensions down the line to identify malicious sites from an independent source. We're not AVG, it's just me. And we also want to create possibly a dnstrace powered DNS server like Quad9 or such things that provide a secure browsing experience for people that can block threats at the network level before they get to grandma, because I don't know about your grandmas, but my grandma's really bad at figuring out what a good Adobe Flash update is and what a bad Adobe Flash update is. And if we can protect my grandma, we can protect yours too. Thank you so much. I wanted this to be an open discussion. We have 60 seconds left. Really? Yeah! All right, awesome. Wow, I thought you guys were going to cut me off. Cool. We have 10 minutes. Please discuss with me. I've not slept. I'm very receptive to questions. Comments, concerns, criticisms, issues, general. Really? All right, yeah.
DNS RPZ. Have you thought about like interacting with RPZ?
We have not. What's RPZ? Oh, sorry. Have we interacted with DNS and RPZ?
Yeah, RPZ is kind of like a firewall for DNS.
Okay.
You might be like, hey, this domain send it somewhere else.
Okay.
You can find a service that has an API for that. You might be able to do that.
So that's the kind of stuff that Pi-hole would do.
Kind of, yeah.
Okay. So, but like at a better scale?
Yeah, I think so.
Oh, that's rad. I am noting that down. That's why I have like I said at the beginning, I have a pen and a notepad. DNS RPZ. Anybody else? Please. Now I'm just standing up here. You can ask me how my day's been.
How's your day been?
Stressful. But it's okay now. Yes. So newly created, like a DNS recency, for example. So like looking at how recently like something is mapped to a given IP. Yeah. Yep. So we actually condense all of our data into the time that we've first seen it and the time that we've last seen it. So actually, it would be very easy to implement that kind of thing, looking at the recency of, well, you know, what time is it right now, and when did we first see this result? So yeah, we definitely could. Do we currently? No. It's a great thing to do, though. So we will definitely be getting on that. Yes?
Thought about using cert transparency for subdomain integration?
So, yeah, so SSL cert transparency?
Yeah.
So Rapid7's datasets actually do that. So Rapid7 has, it's a continuation of SSL Observatory that, yeah, they provide all the SSL certificates that they can find for, I think they do an IPv4 scan of all sites exposing port 443, and then they pull from that. So yes, we do ingest that kind of data, and it's awesome. Other things, more stuff. My League of Legends rank has plummeted because of this. Nothing else? All right, well, this is the last slide. Thank you so much for coming to my talk. It means a lot to me. Keep in touch. I'm here all day. I'm just going to be out in the atrium, probably buying things because I haven't acquired stickers yet. It's 2 p.m., so I'm getting uncomfortable. You can contact me by my email, chris@partridge.tech. You can add me on LinkedIn, please. That's a great resume booster for me. You can chat with me on GitHub, I guess. We'll just like create repositories and then type into the repositories and then submit pull requests. It works for me. Or on Twitter, but I never use Twitter, so good luck. Thank you so much. Enjoy the rest of BSides.